All right, welcome everyone. Going to talk about what I'm working on with New Mars. This is on the code generation for Nock side of things, where we're going to try to convert Nock into something that modern CPU can run and run quickly, and try to eliminate a lot of the overhead that currently exists when we're trying to run Nock right now. Couple quick things. I'm not going to turn on YouTube live chat. I'm just going to have discussion in the New Mars group. If you're not in the New Mars group and think you should be, send me a DM on Urbit. I'm fairly easy to find, but if you can't find me, my patp is ritpub-sipsyl. So with that said, let's dive right in. It probably helps to have a pretty good idea of how Nock is specified in order to go over this. Remember that a Nock program, which we call a formula, is just a noun. So what's a noun? A noun is an atom or a cell. An atom is a natural number, so whole number, 0 or greater than 0, all the way up as big as you want. A cell is an ordered pair of nouns. So a Nock program is just a noun, like any other data we might have on Urbit. So if we are going to analyze, compile, or do anything with Nock formulas, we're going to be dealing with nouns, and the best language for dealing with nouns that I've ever come across is a language some of you might have heard of called Hoon, which also happens to compile to Nock. Specifically, Nock nouns fit one of these patterns starting down here, prefixed with the asterisk, or as we say in Hoon, the tar. This first pattern says if you have a subject and then the head of your formula, so all of these specify A as the subject, meaning the data that the formula will be operating on, and then everything in the tail of this outer cell is the formula. So if the head of the formula is itself a cell, then that means we'll evaluate just that as a formula. So this is what this tar ABC is. We'll use the same subject, we'll evaluate that as a formula, and then we'll take the tail of the cell, evaluate that as a formula, and return a cell of the results. So this is what we often refer to as autocons. You can just write down two formulas in a pair, and you'll get back the pair of their result. Again, we mentioned we run a Nock formula against another noun called the subject. That's what's specified in these A patterns. So Nock 0 is just getting something out of the subject at what we call an axis. An axis is just an atom, so a natural number, where the bits of the atom describe a path through the tree. Go left, go right. So every time we encounter a cell, we look at the next bit in the axis and grab the head of the cell if that bit is 0, the tail of the cell if that bit is 1. If you have bits left over and you try to access an atom, that's an error, that's a crash. So Nock doesn't have exceptions, it doesn't have any kind of fancy error handling mechanism. It either returns a result or it crashes. The next case is where the head of the formula is 1, and in that case we'll just return the tail of the formula as our result. So that's our constant or immediate opcode. We'll skip over 2 for now and go quickly through a few others. 3 is testing whether is evaluating a subformula. So it evaluates B against the subject, and then it tests whether the result of that formula is an atom or a cell, returns 0 if it's a cell, 1 if it's an atom. 4 expects the result of its subformula in B to be an atom. If it's a cell, it will crash. If it's an atom, it will increment that atom. It will add 1 to it and return that as a result. 5 will run 2 subformulas and then test their results for structural equality. So they have the same shape, the same tree structure, the same structure of cells, and all the atoms at the leaves are equal. There's no pointer equality in Nock. We might use it under the hood, but there is no notion of the identity of a noun. There's only structural equality. Nock 6 is our if-then-else construct, so we'll evaluate the subformula B. And if it evaluates to the atom 0, we'll evaluate the subformula C and return its value. If it evaluates to 1, we'll evaluate the subformula D, return its value. Otherwise, we'll crash. And that's the reason for doing this sort of complicated access method, is to actually specify that crash. Nock 7 is the first point where we, aside from Nock 2, which again I said we'll come back to, where we actually skip over we actually alter the subject. So note that we first evaluate B against the current subject, and then we use that in the subject position for our evaluation of C. So this is, we often call this composition. We use the result of B as the subject, the data that's input to the formula C. Nock 8 is similar, except instead of throwing away A after we evaluate B against it, we're going to make a cell with B and A. So we're just going to add the result of B to the existing subject, make a cell, and cons them together, and then run C against that as the subject. We'll skip over 9 once again, because we'll need to talk about 2 to discuss that. 10 looks a little complicated, but if you work through it, it's a tree edit. So this cell here is specifying what edit we're going to do to the tree. So which axis? The axis is the same as we discussed for Nock 0, but instead of reading something from the subject, we're going to put something into a tree. The whole tree is the result of D. So we're just changing a subtree by overwriting it. And then the 2 cases for Nock 11 are dynamic and static hints. Spandrel comments on the name of the file, and yes, the joke is intentional. Dynamic hint actually can affect the semantics of the hinted Nock code in one way, which is to say the argument C here is treated as a subformula, which is evaluated and then its result thrown away. But if the subformula crashes, then the whole formula must also crash. So note here, we actually do run the subformula, and then run the underlying formula, and then take out just the underlying formula as a result. Static hint, on the other hand, is just sort of adding some noun, some static noun of information. Usually it'll be an atom to a formula just to tag it, essentially. So I promised an explanation of Nock 2 and Nock 9. So Nock does not have a notion of a procedure call. And this is probably the biggest challenge in actually attempting to make Nock performant. If you're familiar with JavaScript, Nock does not have function invocation where you write the name of the function and then some parentheses and some arguments. Instead, it has eval. which means that we are actually passing data to it that we expect to be treated as a program rather than a label for some statically known, already generated program. This is expressed most generally in the Nock 2 opcode, where we have two subformulas. We evaluate them each against the subject, so AB here and AC here. We treat the result of B as the new subject and the result of C as the new formula. So note, we are dynamically computing a new formula to run here, and we could put any arbitrary computation in C. We don't very often use Nock 2. Whom will generate Nock 2 for the .tar rune, and I think of one or two other places. But otherwise, you will not usually see Nock 2, but it is used in the specification of Nock 9. And if we go through this a little bit, we're evaluating the formula C, which we expect to return what we call a core. So a core is, in general, a pair of a battery and some context. The battery goes in the head and is some noun which contains formulas, and the context is other data which those formulas might want to reference. So C will return a core. We'll then treat that core as the subject. We will, for a 2, where the subject computation of the 2 is 0, 1, so take the whole subject. 1 is 1 as an axis means the whole subject. And then we will go down to the axis B in the core and treat that as a formula. So notably, the formula now has the ability to reference itself because we got the formula out of the core, but the whole core is in its subject, so it can go find itself again in the subject. So basically, every procedure or library-like construct in Hoon is a core. Any rune that starts with a bar is making a core. So if you write bar sen and then you have a bunch of lus arms, that's a core with many formulas in it, but it will have that whole core as its context, as well as anything that was already in the subject when you create at the point where you wrote the bar sen expression. If you make a gate, that is a special core with one arm in its battery. So the arm is at axis 2, and where we've added a slot in the context, so the head of the context, so the head of the tail of the core, or axis 6, which we call the sample. And this is how we construct something resembling a procedure call in Hoon, is we actually edit the core using Nock 10. So you will see 10 where the axis is 6 and put in the argument as the patch. And then on that edited core, we will call Nock 9 with axis 2, and that formula then will be able to access the sample in axis 6 at its subject. So this is how we pass arguments to gates, and more generally, a core that has a sample but many arms is a door, and this is also how we pass arguments into a door. The problem here is, again, in both of these cases, in C here and in C here, there's entirely general computation possible to come up with the code that we're going to run. There's no way, in the most general sense, to know what we're going to run ahead of time, which means we actually, in general, have to branch when we look at the formula and say, did we already generate code for this? Where is it? Or did we not, and now we need to go generate code for this? Resolving that in most cases is the job of subject knowledge analysis, which we won't go over in detail today. But suffice to say, we can have a running conservative heuristic that is able to say what we know about what a formula will generate and what its subject will be. And then if that knowledge includes knowledge of what the result of this formula generating expression will be, then we can statically compile a procedure call in the underlying code. And this looks like it will work fairly well for most cases. There's a few cases where some extra information needs to be threaded through. But what we are going to talk about today is something called destination-driven code generation. This was a paper in the late 1980s by Kent Dybvig of Shea Scheme when he was at Indiana University. The premise was essentially that you should pass information down as you recurse over the ASD. So remember, most of these formulas take subformulas. So Nock is in general a fairly deeply nested tree. So we're going to recurse structurally over this tree as we generate code. And as we do so, we're actually going to pass information down in order to give the code generator context for what we're actually trying to do. And we're going to pass two kinds of information down, two different destinations. We're going to pass a data destination, which is to say this subformula will have some result, and a code destination, which is to say, or a control flow destination, which is to say when you're done running this code, what code will you be running next? This allows us to do a few things. First of all, it generalizes over a mode for tail position. So if what you're doing after this code is return, then you're in tail position. Otherwise, you're not in tail position. It also gives you a way to elide repeated branch statements. So for example, if we have a Nock 6 where the test formula is a Nock 3, if we compile that naively, that will turn into two branch statements. One branch statement will do some bit arithmetic on the underlying representation of a noun at the machine level to see if it's a cell, and will then branch to either an immediate 0 if it is a cell, or an immediate 1 if it's an atom. And then we will branch on whether that result is a 0 or a 1 in order to decide which branch to flow through to in 6. With destination-driven code generation, if you are when you generate the test expression for a conditional, you actually pass in a pair of labels for the true code and for the true branch and the false branch. And by inspecting the control flow destination and seeing, oh, this is actually a pair of labels, you can branch directly to these branches without ever generating the 0 or 1 and then re-inspecting it. Or if the result of that test condition is also used elsewhere, you can branch and generate an immediate 0 or an immediate 1 followed by a direct jump to these labels, or even just prefix these labels with an immediate 0 or 1 to the proper data destination. So there's only one branch involved for one Nock 6 as opposed to usually 2 and possibly more. Similar sort of thing obtains for Nock 5, the quality check. But the more exciting thing is the data destination idea, because what this will let us do is keep track of all of the axes we touch with Nock 0 Nock 9, Nock 10 in a Nock formula, and we can use this information later on. We won't talk about in detail how we do this today, but just note that by keeping track of this, what axes we're touching, we then have the information we need to registerize the linearize Nock program, meaning that we can assign virtual registers in our underlying compiler backends IR to axes in the subject or to axes in a result noun, and then allow the register allocator, whether it's Crane Lift's register allocator or LLVM's register allocator, whatever we're using in our backend, to allocate those virtual registers to physical CPU registers, which means that we can eliminate a lot of the pointer chasing and new cell allocation involved in looking up or editing axes. Combined with subject knowledge analysis, doing things like turning loops into static jumps, turning procedure calls into static calls instead of dynamic evals. This gets us extremely close to Hoon code, turning into, at the machine level, something that looks like it came out of a C compiler. So a TISDOT in Hoon has a high likelihood of turning into a register mutation in assembler rather than a bunch of new cell allocations to an axis. So diving into the code itself, the way we're going to structure the data destinations is we're going to imagine that we have a sort of mutable noun that our linearized Nock code is reading from and writing to. So we imagine we have a machine that where the register state is actually just this mutable noun, and it takes these instructions in sequence to run a procedure. So the most general one for the mutable noun is the move instruction, which just copies some axis in this mutable noun to some other axis in this mutable noun. The other would be an immediate, where we have some noun sort of written down in our code, and we're going to write that to an axis. We can check if something's a cell and branch to a label if it is or if it isn't. We can increment an atom at an axis. We can check equality. Axes 4 and 9 are the head and tail of axis 4. So we're going to leave the subject at axis 3. The tail of the outermost cell. We're going to use axis 4 as sort of our default return and result destination. And that's the head of the head, and the head of the tail will be sort of our save location. So axes 8 and 9 are the head and tail, respectively, of axis 4. So the head is always multiplied by 2, and the tail is always multiplied by 2 and add 1. We can branch on a what we call looping, a Boolean, but where 0 is true and 1 is false. We have labels and unconditional jumps to labels, static call that pushes onto the stack and then returns to the same place, static jump that just jumps. This is how we do tail calls. We're done with this formula, return its result from axis 4. And then these are the equivalent of call and jump, but where we don't statically know the formula, and so we have to just call out to the code generator and say, hey, look at what's there when we get there and generate code for it. So moving over to the right side of the screen, there's a whole bunch of state, but for the destination-driven code generation stuff, the destinations are here in air. That's the control flow. And veil, this is the destination for data flow. We never want to set our destination to be directly somewhere in 5 because that's where we're saving stuff. So we just have an assertion to check that. The easiest case is Nock 0, where we're just looking something up in the axis. Remember, we put our subject in 3, and this is an axis in the subject. So peg is in the Hoon standard library. This just composes the axes. So we look at this. We look at the subject and move from an axis in the subject, again under 3, and to wherever our data destination is. And then bail does two things. It checks if we're in tail position and inserts a return statement if we are. If we're not in tail position, it checks if we have branching control flow and then inserts a branch based on our result. So this would be like if you wrote a conditional on some value you'd saved in a face in your Hoon subject. So you run a test, you save the result somewhere, and then you branch on it later. And then this at the bottom is just doing the subject knowledge analysis for this case. One is very similar, except in the case where we have a branching instruction, because we're writing down statically the value, we can say statically jump to one branch or the other if it's 0 or 1, or crash if it's neither 0 nor 1 and we're in a branching state. Because we know, so we can just generate an explicit crash because we know at runtime it should crash anyway. Otherwise, we're just going to check if we're in tail position and write a return if we are. And again, the subject knowledge for constant is very simple. We know it won't. We know it won't crash. We know what it is because it's right there in the code. Another interesting case is 5, because here we see that, remember, this instruction compares the two immediate children of axis 4. So we want to run the sub expression with its we want to run the sub expression so that we write its results in there. We're going to write the first result into 4 and then save it because we might overwrite 4 while we're evaluating the second one. We'll have the second one write directly into axis 9, and then when we do this sift, this is a save shift, axis 4 will move to axis 10, which is the head of axis 5. So we'll pull that back out into axis 8, which is the head of axis 4. So now we have the result of this at 8, the result of this at 9. We can throw away what we saved earlier and insert the test instruction. Axis or 6 is kind of complicated, but note here that this is where we pass this the the BAB case is the branching case for control flow. So we're saying here your control flow needs to flow to either true or false, depending on what your result is. And then we'll go on to generate the underlying code. Nock 7 is an interesting case because we're going to reset the value destination. Remember, we said the subject goes in axis 3 of this mutable noun. So when we run the computation for the subject, we're just going to ask it to write directly into the subject. But first we're going to run this hide computation, which saves the subject into that same save arena that we earlier used to save a result. This has stack-like semantics, but notably we're not actually going to push into the activation frame directly. Our register allocator might do that for us, but we're actually going to be shifting virtual registers around in a table, mapping them to axes, meaning that if we don't actually use something that we saved in this way later, then the liveness of that virtual register will not extend over this, and the register allocator will not bother to save it in the activation frame, which is exactly the behavior that we want. So we can be very conservative at this layer about saving things, and a layer lower down we'll be able to see whether or not we actually use values that we saved and know exactly how long to save them for, or if it needs to save them at all. So Nock 8 will, because it needs to use the subject and then write to the subject, but save it, will actually write into the head of the result register and then copy the subject to the tail, thus creating a whole cell for the subject, and then put the result back in 3. Notice we don't do a hide here because the whole subject is still present there. So to put the subject back, we'll actually just take the tail of the subject and move it to the subject and just throw away that head from earlier. And again, this is fine. This move will turn into a no-op if the register allocator determines that we don't actually use this value afterwards. So I think we're a little past time. I don't see any questions in the chat stream, but I hope this was a little bit of a good illustration as to what I'm working on. This code actually compiles and runs as it exists, pushed into GitHub. I've made a couple of modifications this morning, but they're mostly trivial formatting modifications, and I'm starting to work on this idea of actually assigning IR registers to axes in this mutable noun so that something like crane lift or LLVM can actually allocate all of the machine's registers in a useful way for use in Nock computation. So with that, I'll